Video 51 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is frequency-dependent and spectral properties, as well as time-dependent fields. So far, we have only discussed properties which arise due to the interaction with static electric and magnetic fields. But if we want to discuss the interaction of molecules with light or electromagnetic radiation in general, then we have to consider time-dependent electric and magnetic fields. So some of the properties which we are going to discuss in this chapter, like the frequency-dependent polarizability, are generalizations to the time or the frequency-dependent case of the corresponding static properties, the dipole polarizability. But we are going to discuss also properties, in particular electronic excitation energies and transition dipole moments, which we cannot derive as derivatives of the ground state energy, but we can anyway obtain them from the linear response function which we had defined and derived in chapter 3. But before we are going to look at the molecular properties, I want first to discuss the electric and magnetic fields, or the vector potential for the time-dependent or frequency-dependent case. So let's consider a plane electromagnetic wave, also called linear polarized electromagnetic wave, which is oscillating with an angular frequency omega. And what is the expression for the vector potential for such a wave? Now, we can get that by solving Maxwell's equations, and you're going to look at that, that this is actually a solution to Maxwell's equations. So here we have the vector potential as a function of position and time, and there are two contributions. Here we have the amplitude of our wave, which is perpendicular to the propagation direction of the wave. The propagation direction of the wave is given by the so-called wave vector or propagation vector. So this points in the direction of motion of the wave. The length of this propagation vector is actually related to the frequency of the oscillation, or if you want to express in terms of the wavelength of our wave, and it's also related to the refractive index of the medium in which the wave is propagated. So this is the refractive index of the medium, which depends on the frequency of our wave. And this dependence of the refractive index of the frequency of the wave is called the dispersion. If the medium in which our electromagnetic wave is propagating is actually vacuum, then the refractive index is going to be 1. Because the refractive index actually is just the ratio of the speed of the electromagnetic radiation in vacuum to the speed of the radiation in the medium. If it's purely imaginary, then taking the complex conjugate of the amplitude means that it's just a minus sign. So we can combine the two exponentials here with a minus sign. And now this amplitude of is in general a complex vector, perpendicular to the propagation direction, but could be complex. But by choosing an appropriate origin of the time variable, we can make it purely imaginary, which then of course means that we actually end up with this expression with the sinus by using Otto's rule. And so we have sinus here. This is imaginary. We still have an I in front of it, which means that by this smart choice, then our vector potential itself becomes real. Now, knowing the vector potential and having our relations between the potentials and the electromagnetic fields, we can now derive expression for the electric and for the magnetic field. The electric field, please remember from chapter 2 of the book, as the time derivative of the vector potential. So taking the time derivative of this, gives this expression here. We get cosine, where the amplitude of the electric field then is I times 2 times omega times the amplitude of the vector potential. And the magnetic field, well, the magnetic field is the curl of the vector potential. We still get cosine, but the amplitude of the magnetic field now is then 2 times I times the cross product of the propagation vector and the amplitude of the vector potential. And the amplitude of the electric field is perpendicular to the wave vector, whereas the amplitude of the magnetic field is not only perpendicular to the wave vector, but is also perpendicular to the amplitude of the electric field. So the electromagnetic fields are perpendicular and are oscillating in perpendicular planes. This was for one wave. If we now have a general pulse of coherent but polychromatic electromagnetic waves or radiation, we can write that as a superposition of this monochromatic plane waves. And in the extreme, we can write it, of course, as an integral over all frequencies. So here we have the vector potential for this, which is then an integral over all frequencies. Here with the same expression before, and for each frequency we have a different amplitude. And if it's just a finite number of frequencies, then of course most of the amplitudes for most of the other frequencies are then zero. Now the sinus I can of course rewrite again with making use of Euler's rule by this negative combination of the two exponential functions, and correspondingly for the electric and magnetic field component of the electromagnetic radiation, I get these expressions, which are just the integrals over what we had for the monochromatic wave. Now R here is the position vector where of course we're interested to know the value of the vector potential or the electric and magnetic fields. And if you look at the interaction of a molecule with radiation, we typically would choose the origin somewhere in the molecule. And then we're interested in the values of the electric and the magnetic field, of course, at all points within the molecule, which means that this position vector R has at most a length which corresponds to sort of the radius of our molecule, or the diameter x, or in the worst case, if I put the origin of the coordinate system in one end of the molecule, then it would be the diameter of our molecule. Now, typical molecules have diameters of about 1 to 100 angstroms, which thus means that the maximum length, the typical maximum length of this vector R is in this order, 1 to 100 angstroms. The propagation vector, as we said before, has a length of 2 pi divided by lambda in the case we're talking about vacuum. Which means if we then look at the product of this propagation vector and our radius, or the length of this product, we can see that this is much smaller than 1 for all types of electromagnetic radiation, with wavelengths longer than X-rays. So let's look at the position-dependent part of these exponentials here. So e to the I, and then the product of the position vector times the radius. So let's look at that now and use the normal power series expansion of an exponential, which is like this here. But if the product of k with r, the scalar product of k with r, is much smaller than 1, then of course we can approximate this. I mean, we can stop after the first term because everything which comes afterwards is much smaller than 1, and can approximate it just by approximately 1. That, of course, means that our wave has, over the extent of the molecule, no spatial variation any longer. Essentially, this means also that k is equal to 0 then, or we approximate k as being equal to 0. So over the extent of the molecule, there is no significant variation in the electric or magnetic field for a given point in time. So we can therefore write the vector potential without the e to the ikr term. We just have the frequency dependent terms like this. So we can write it as a simple sinus of the frequency times time, or the here the difference of the two exponentials, and correspondingly for the electric field like this. The magnetic induction actually, however, becomes a magnetic induction which only would depend on time, vanishes, meaning it becomes zero because it's the curl of the vector potential, and the curl means it includes spatial derivatives, but since the vector potential only depends on time, of course, its spatial derivative is zero. You could also look at it this way, that the amplitude of the magnetic field was the cross product of the wave vector and the amplitude of the vector potential, but since we have the wave vector to be equal to zero in this situation, the amplitude of the magnetic field becomes zero then. In chapter 2.9, we already discussed such a purely time-dependent vector potential. And we saw that we can use two different gauges. We can use the length gauge or the velocity gauge. And in the length gauge, then we saw that the perturbation Hamiltonian becomes then simply minus the dipole moment operator times the only time-dependent electric field then. And since this electric dipole moment operator appears here, or the interaction is described with the including the electric dipole moment operator, one often calls this long wavelength approximation, because we assume that the wavelength is so long that the wavelength of the radiation, that over the extent of the molecule there's no spatial variation anymore. One calls this long wavelength approximation also the dipole approximation. Now, if one would keep the next term in the expansion of the exponential here, which is I times the scalar product of the wave vector with the position vector, that then leads to a spatial non-uniform vector potential and electric field, and it will also mean that the magnetic induction doesn't vanish any longer. And the operators which you then will get, you will then of course get an interaction with a molecule via the magnetic dipole moment operator, and since we have now a non-uniform vector potential and therefore a non-uniform electric field also, we will get the electric quadrupole operators. So this was plane or linear polarized radiation, either monochromatic or polychromatic. But later on, for one of the properties, optical rotation, we need to consider not only plane polarized wave, but left and right circularly polarized electromagnetic radiation. And the difference is, of course, in plane, linear polarized electromagnetic wave, the electric field oscillates in one fixed plane, and the orientation of that plane doesn't change while the wave is propagating, and the magnetic field is then oscillating in a plane perpendicular to that. Whereas in left and circularly polarized radiation or light, the plane of oscillation of the electric field and corresponding to the magnetic field vectors rotates. And in right circularly polarized light, the plane rotates clockwise when you look into the incoming wave. So if you look at the origin of where the wave comes from, and you see that the plane of the oscillation of the electric or the magnetic field turns to the right clockwise, then it's right circularly polarized light, and if it's turning anti-clockwise, it's called left circularly polarized light. Now, how can we describe this? Well, we have to sort of change the direction of the oscillation depending on the position, therefore. And you can do that with this form here, where EI, EJ, and EK are unit vectors along the three axis. So the EI is perpendicular to EJ, and both are perpendicular to EK. And EK is the unit vector in the direction of the propagation, and EI and EJ are unit vectors perpendicular to this direction of propagation. And so the electric field can then be written in this form, where we have the cosine in one direction, and then we have a sine of the basically the same expression for the perpendicular direction. And this is for the left one, and for the right one, the same, just you have a minus sign here now. And if you would calculate values of this field, you will see that they actually rotate, the planes rotate in this way. The associated magnetic induction vectors are similar then, except that the cosine becomes to a sine and vice versa. These two forms of radiation, the right and left circularly polarized radiation, are also interesting because they're related to what is called helicity, which is the projection of the photon's spin on the direction of propagation. And the direction of propagation we're normally called z, so it's the z component. And left and circularly polarized photons are actually the ones which have a well-defined value of this helicity. So they're actually sort of eigenfunction to the spin operator for photons. And it's the case that the right circularly polarized photons, meaning where the electric magnetic fields are described by what we had before, correspond to the ms-1 value, and the left circularly polarized photons or radiation correspond to the ms+1 value. The ms0 value doesn't exist because we have with a particle, or we have with a particle to do which has no rest mass. Now, a combination superposition of left and right circularly polarized waves, as long as they both have the same refractive index, so if the refractive index of left and right circularly polarized light are the same, and we just let it call without the index for right and left. So a linear a superposition of such two waves then actually gives us this expression, and which is simply just the expression for linear or plane polarized light. Which means that plane polarized radiation is actually just a superposition of right and left circularly polarized radiation. And that actually means its spin has no well-defined value. The average, of course, is going to be zero again, but it's not an eigenstate of the spin of photons.